What if I told you just 5 principles can make your code flexible, maintainable, and easy to understand? Yes, I'm talking about solid principles. Here I will simplify solid principles for you so you can quickly learn and brush up this in such a way so you will never forget this. So without waiting, let's start. In this series, first of all, we'll talk about single responsibility principle. It says a class should have only one reason to change. Why? If a class is handling too many things, it becomes bulky and hard to maintain and update. One fix may break another. Have you ever seen in class 10 kids sitting from different classes? No, right? It doesn't make any sense. Now let's see some code to understand this better. Here is a single class doing too much things. It's breaking single responsibility principle. An employee class here is trying to save an employee and also trying to calculate the salary. Later you might need to add some more things like leave, benefits, etc. here, and it will become an accident-prone zone. Now let's see a better implementation for this. Now look at this class which is responsible for creating an employee and getting employee details. So it's about employee-specific things. To calculate salary, we have a different class here. Similarly, if we want to add other features like benefits, leave management, etc., we can create a separate class for this. This way, you can keep your code clean and maintainable. This adheres single responsibility principle. You can pause the video and read some more theoretical parts like benefits, etc. So one class, one job. That's single responsibility principle. The next is open-close principle. It says classes should be open for extension but closed for modifications. Why it says? Because if you are changing a class to add new features in it, there are chances that you may break existing feature. It becomes a bug-prone zone even for future. Just think of a monitor. Would you like to open the monitor with a screwdriver and add battery or CPU inside it? No, right? Rather, you may extend the monitor by adding external CPU or external battery to make it a complete PC. Now let's see a code example for open-close principle. Look at this notification class. It has a method sendNotification, which is responsible for sending many types of notifications like email, SMS. Every time you add a new notification type, you will need to modify this class, and that violates open-close principle. Let's see how to fix it. To fix this, we will use an interface called iNotification. It has a declaration for send. And now we will create a separate email notification class where we will implement the iNotification interface, and it will have its own definition here. Similarly, for SMS notification, we will implement the iNotification interface and it will have its own definition. Similarly, if you want to introduce any new notification services, you can add a new class. It will extend but not modify the existing class. This code is following the open-closed principle. Add new features without changing old code. That's open-closed principle. Now we'll talk about Liskov substitution principle, which is most confusing, but after watching this, it will be never confusing anymore. It says a subtype should be substitutable for base type. In other words, if class D is a subclass of class A, we should be able to replace A with B without breaking the program. Means the derived class should behave properly when used in place of the base classes. Let's understand this in code first. Let's try to understand the statement I gave for Liskov substitution principle. As per Liskov substitution principle, the derived class should be able to replace the base class without affecting the functionality of the program. In the code below, the derived class tiger is not able to replace the base class animal. Tiger is also an animal, but tiger can eat, walk, but tiger cannot be groomed, and this is throwing an exception here. You may think that we can simply not throw here and log the error, but it will break another solid principle about which we will talk in a bit. In other hand, dog and eat can be groomed, so it's able to satisfy the animal's base class. But the tiger class is not able to justify the animal's base class, and that is violating Liskov substitution principle. Look at the statement once again. Derived class should behave properly when used in place of base class. And now look at the tiger class, which is inheriting the animal's base class. Does it work perfectly? No, it's breaking because tiger cannot be groomed. So now let's see how we can fix this. To fix this, first of all, we will break the abstraction. We have created a iAnimals interface, which has the basic feature of animals. Either social or wild animals, both can walk. Now we have created abstractions for specific features like social animal can be groomed and wild animals can hunt. And now look at the tiger class and also the dog class. Both are able to satisfy the base class, I animal and a social animal for dog and wild animals for tiger. So now it's satisfying the Liskov substitution principle. To remember this, just remember that a dog and a tiger cannot sit in your home. A dog needs to be at your home, but the tiger needs to be at any forest. You cannot create a single or similar space for both animals. Pause and read more theoretical aspects about LSP. So don't make child classes that break the behavior of parent. That's Liskov's substitution principle. Next is interface segregation principle. It says don't force a class to implement a method that it doesn't need. In other words, create smaller, more specific interfaces so that classes only implement what they actually use. Why? To keep your interfaces clean, and without ISP, classes are forced to implement methods that they don't even need. Think of your backpack. Will you ever keep items in your backpack which you never use? No, right? Now let's see a code example. Look at this code. There is a one interface I printer which has print, scan and fax features. A basic printer also implements iPrinter, and now it is forced to implement a scan and fax feature as well, which actually doesn't have. Basic printer doesn't support scanning and fax. In other hand, advanced printer implements iPrinter interface and it has all the functionalities, so it's working good. But for the basic printer, the ISP breaks. Now let's see how to fix it. For that, first of all, we will segregate the interfaces. First of all, basic printer with all the basic features like print and turning off and on. Then for a scanner, a different interface, and for fax, a different interface. Now look at the classes. The basic printer and the advanced printer both are now in good shape and happy. So this is following the interface segregation principle, where we have segregated the interfaces. Pause the video to read more theoretical aspects of interface segregation principle. So don't force people or classes to do things that they don't know how to do. Give them only what they need. That's all about interface segregation principle. Now let's talk about the last, dependency inversion principle. It says high-level modules should not depend on low-level modules, but should depend on abstractions. Why? It helps to remove tight coupling and introduces loose coupling via interfaces. Think of your Netflix content. You don't depend on a TV, laptop, or mobile phone to watch a movie. You just need a screen and the content gets delivered on the same screen resolution perfectly. You cannot depend on a single device screen here like TV or laptop. Let's see core examples. Look at this class LED TV. It can play a content. So now if the class movie and audio songs needs to play a content, it is directly dependent on the LED TV. If we want to change this class LED TV, we will need to change the implementation at movie and audio songs class as well. So it doesn't matter how many classes have implemented this LED TV class, we will need to make changes to all the classes which has this implementation, and that's a bad design. Now let's see how this can be fixed. This can be fixed using or introducing a dependency injection here. And that is an example of dependency inversion principle. So let's introduce an iScreen interface first, and then this interface has a method play content. Now all the low-level modules like the LED TV, mobile phone, or the projector screen can implement this iScreen, which has play content feature. And then high-level modules such as the movie and the audio songs here, we will inject the abstraction, we will inject the interface here. So now further we need to register the dependency injection. In case of .NET Core, we can do it as startup.cs using services.and, add transient, scoped, and singleton. Now if we need to implement another screen, we can simply introduce a new class, or even by changing the low-level module, it won't break the high-level modules. Now we can see here that high-level modules are not dependent on low-level modules, but both are dependent on the interface iScreen. So this is satisfying here dependency inversion principle. So DIP makes your code flexible, testable, and ready for future changes by depending on abstraction. Now if you need clarity or anything, do let me know in the comment box. If you found this content helpful, please like, subscribe, and share it with your friends. And don't forget to hit the bell icon so you never miss a new video. Thank you so much for watching. See you in next video. Bye for now.